Have you ever been like completely frustrated when an AI assistant remembers a really, really specific fact you told it weeks ago, but then it completely misses the obvious context of a conversation you're having right now?
Oh, absolutely. It happens all the time.
Right. Like, say you're looking for parking downtown, and it's suddenly bringing up the exact model of your old Honda Civic instead of, actually helping you find a garage nearby. It's maddening.
It really is. And, well, it's a perfect example of the massive disconnect between how machines store data and how human beings actually experience memory.
Yeah, totally.
We expect our assistants to, understand the flow of our lives, to grasp the nuance of our current situation, not just act as this literal-minded digital tape recorder.
Exactly. A tape recorder is exactly what it feels like. And that gap, that specific gap between expectation and reality is exactly what we are tackling in today's deep dive.
It's a great topic.
We are looking at a state-of-the-art generative AI paper from researchers at Tencent. It's titled T-Mem, Memory that Anticipates, Not Archives. And our mission today is to really uncover how these researchers are finally teaching AI to remember things the way you and I do.
Right, which is huge.
Yeah, not just by archiving past facts in a database, but by actively anticipating future needs. Looking through this source material, this really stood out to me as the potential missing puzzle piece for truly smart, long-term AI companions.
Oh, I totally agree. It's certainly a paradigm shift in the architecture. If we just strip it down to the core premise, this paper is mapping out the transition from a world of strictly descriptive memory to a world of associative memory.
Associative memory, right?
Exactly. And that distinction, it fundamentally changes how an AI agent is going to interact with you over months or even, years of continuous conversation.
Okay, let's unpack this. Because to understand why T-Mem is such a massive breakthrough, we really need to understand exactly why current AI memory systems are, collectively failing us in these long-term scenarios.
Right. And to understand the failure, we really have to look at the mechanism operating underneath it all.
Okay.
The prevailing long-term memory systems we have right now, and this includes pretty much everything from flat RAG, which stands for retrieval augmented generation, to structured systems like graph RAG, or even operating system-style memory architectures like MEMGPT.
So basically all the big ones.
Exactly.
Yeah.
All the heavy hitters. They all essentially rely on one foundational trick, which is similarity search.
Similarity search, meaning the system is fundamentally just looking for things that look like other things.
Precisely. Yeah. They might use lexical searches like a system called BM25, which basically looks for exact keyword matches.
Like Control F on a document.
Yeah, exactly like that. Or they might use dense vector embeddings, which project your question and the stored memories into this mathematical similarity space.
Oh, right, the vector space thing.
Yeah, so imagine turning every single sentence into a set of coordinates on a giant multi-dimensional map. The system then just grabs the memory that sits geometrically nearest to your current prompt.
Makes sense.
And it works beautifully, but only if your current query shares surface features with the stored memory, like the exact same wording or the same named entities.
Okay, I think I've got a good analogy for this. So it's basically like a literal-minded filing clerk. You hand this clerk a label, and they sprint into the back room, and they can only find a document if the exact same words are written on the tab, right?
That is a very apt analogy, yeah.
So if you ask for quarterly financials and the folder in the back says Q3 money stuff, the clerk just comes back empty-handed. They're just staring blankly at you because the literal letters don't match.
That's exactly it. The system is entirely reachability bounded by that surface similarity. Yeah. It can only reach what it can explicitly match. Let's look at the classic example the researchers highlight in the paper just to show where this breaks down in real life.
Yeah, let's hear it.
Imagine, say, a month ago, you casually mentioned to your AI assistant, a colleague on my team has a serious seafood allergy.
A very normal passing piece of information you might share during a workday chat. You wouldn't think twice about it.
Exactly. Now, jump to today. You ask your AI, where should we take the team for dinner tonight? Under the current prevailing memory systems, the AI is almost guaranteed to fail to bring up the allergy.
Because the clerk, our filing clerk, is looking for the words team, dinner, tonight, or restaurant.
Right.
And the original memory says colleague, seafood, and allergy. Zero surface level overlap there. The lexical similarity is basically zero. And even on that mathematical vector map you mentioned, allergy and dinner might not be close enough to trigger a match.
Exactly. What's fascinating here is that the AI completely misses what the researchers call the latent semantic arc.
Latent semantic arc.
Yeah, so There is a glaringly obvious logical connection between knowing someone has a seafood allergy and the action of picking a restaurant for that person.
I mean, to a human, yeah, it's obvious.
Right, but because the target memory surface form has drifted entirely away from the current question, it can never be found using a simple similarity search. The researchers identify this specifically as the associative blind spot. All of these prevailing systems collectively fail right here.
The associative blind spot, that perfectly describes that frustrating feeling we started the deep dive with. The AI is just blind to the association, even though to any human it makes complete sense.
Yes.
Which brings us to the really big question. If similarity search is fundamentally broken for these types of relational, context-heavy questions, how do we fix it? We have to look at how the human brain actually handles this, right?
We do. And this is where the paper draws heavy inspiration from cognitive science. Specifically, it leans on a concept called episodic future thinking.
Episodic future thinking. Oh, I've heard of episodic memory, remembering specific events from the past, but episodic future thinking sounds like something else entirely.
It's a really fundamental cognitive trait. As humans, we don't just passively store memories like a hard drive. We don't just put the file in the cabinet and wait for someone to specifically ask for it.
Right, we're not just archiving.
Exactly. Instead, when we experience something, we actively rehearse that past experience for the future context in which we might actually need it.
Oh, I see. So when my coworker says they have a seafood allergy, I'm not just writing down a sterile fact like Bob equals no shrimp.
No, you're not.
My brain is automatically doing this little simulation, projecting forward. I'm thinking, oh, if I ever have to book a lunch with Bob, or if we go to a conference together, I need to make sure we avoid the sushi place.
That's exactly it. You are rehearsing the past experience for a future cue. You are binding the memory to a situation where knowing it will actually have utility rather than just binding it to the literal words that were spoken at the time.
Here's where it gets really interesting because that is a clever structural shift. It moves the heavy lifting to the right phase. And reading this paper, it seems T-Mem actually engineers this exact human cognitive quirk right into the AI.
Yes, they do.
They don't just save the raw text of the memory, they perform what they call right-time rehearsals, creating metadata they refer to as triggers.
Triggers, exactly.
So at the exact moment the AI learns a new fact, instead of just archiving it blindly, the AI pauses and essentially asks itself, like, how might the user ask about this later?
It creates a structural decoupling. It completely separates what makes a memory reachable from what counts as the actual evidence when it's time to give an answer.
But let me push back on this for a second,
Sure.
because thinking through the actual mechanics of this, I have a major question. Is the AI just aggressively pre-tagging every single conversation with random guesses about the future?
What do you mean?
Like, say I tell it I bought a dog. Is it just going, maybe they will ask about dog food, or maybe they'll ask about vacuum cleaners for pet hair, or maybe noise complaints? If it's just hallucinating dozens of potential futures every time I speak, that sounds chaotic and honestly, potentially disastrous for compute costs.
That's a crucial point, and it's exactly why T-Mem is so meticulously engineered. It is not just taking wild, unconstrained guesses.
Okay, good.
First, it maps these triggers onto a highly structured retrieval space. And second, it generates these triggers by leaning on the large language model's own vast pre-trained semantic understanding of the world.
Okay, so because the core LLM has basically read the entire internet, it already inherently knows that, say, seafood allergy is semantically linked to restaurant reservations and dining out.
Right.
It uses that underlying logic to purposefully generate the trigger rather than just throwing darts at a board.
Precisely. It brings that latent knowledge to the surface right at right time. And to keep it organized, T-Mem places these triggers into a 2x2 design space. It operates across two axes: granularity and orientation.
Let's map this grid out so you as the listener can really picture it. Looking at this design space, it seems the first axis is granularity, meaning the AI has to decide if it's logging a single isolated fact, which they call an item, or a broader contextual piece of dialogue, which they call a scene.
That's right. It asks, does the query require a single highly specific atomic fact? For instance, if you ask, what day is my flight to Tokyo?
That's an item.
Exactly. It's a discrete piece of data. On the other hand, does the query need the broader context of an entire conversation? Like, what were my main concerns when we discussed the Tokyo itinerary last week?
Oh, I see.
Yeah, that requires pulling an entire scene, a cohesive stretch of dialogue that captures a broader mood or a multi-part plan. So that's the vertical axis. Item versus scene.
Got it. Item is a single fact. Scene is a whole vibe or flow of conversation. And looking at the horizontal axis, we have orientation. Now, this deals directly with what we were discussing earlier about similarity search, right?
Yes. Orientation asks, is the memory descriptive, meaning it shares surface words and clear entities with the query? Or is it associative, meaning it is bound only by that latent logical connection we talked about, like the allergy to the restaurant?
So we have a 2x2 grid. Item and scene on the vertical, descriptive and associative on the horizontal.
Yes.
This creates 4 distinct spaces, and T-Mem creates a specific type of trigger for each one of those 4 spaces. If we know similarity search works fine for exact words, T-Mem still lets the AI do that by creating what they call entity or scene triggers on the descriptive side.
Correct. So the entity trigger handles the item-level descriptive space.
Yeah.
It simply names the specific item with a superordinate, broader concept.
It's a superordinate concept.
Yeah. So if you mention buying a specific brand of hiking boots, the entity trigger might tag that memory with outdoor footwear or hiking gear. It just expands the surface level net just enough to catch a direct question later.
Nice and simple. And for the scene-level descriptive space, we have the scene trigger. This is for when we are looking at a whole conversation and trying to match it to words you might use later to describe that specific event.
Right. And for this, the AI actually describes the current scene along 4 distinct attributes: the situation, the objects involved, the event taking place, and the emotions expressed.
Oh, that's thorough.
It summarizes 1 sentence for each. Imagine you vent to your AI for 20 minutes about a frustrating, delayed project launch at work.
We've all been there.
Yeah. The scene trigger creates a rich, structured summary noting the project delay event, the stressful emotion, the workplace situation. It gives a future similarity search a lot of very clean surface area to grab onto.
Okay, so those 2 triggers, the entity and the scene, they are handling the descriptive side. They are basically taking things AI is already somewhat decent at and just making them much more robust.
Exactly.
But the real magic happens when we cross over into the associative half of the grid. This directly addresses that structural blind spot we were talking about. Let's look at the item-level associative space, connecting a specific fact to totally different future context.
This is where the bridge trigger comes in.
A bridge trigger.
Yeah. It actively projects a fact into a situation where knowing that fact would matter. This brings us right back to your seafood allergy example.
Okay, how does it handle that?
When you mention the allergy, the system actively generates a bridge trigger that explicitly says, this fact is relevant if the user ever asks about dining out, restaurant choices, or event catering. It builds a literal bridge from the isolated fact to its future situational utility.
It's doing that episodic future thinking we talked about. And finally, we have the scene-level associative space. Honestly, this seems like the hardest one. Taking an entire past conversation with all its messiness and nuance and connecting it to a future situation that uses totally different words.
It is complex. They call this one the horizon trigger. It projects a past scene onto forward-looking dimensions. It essentially asks, how might the underlying theme of this entire situation evolve or become relevant later?
Give me an example of that.
Sure. If you spend an evening talking to your AI about how much you hate the cold weather and how exhausted you feel in the winter, the horizon trigger might log a forward-looking dimension like relevant for future travel planning, specifically suggesting warm weather destinations or winter escapes.
That is fascinating. It's taking the abstract feeling of a conversation and tying it to a concrete future action. And as the paper points out, prevailing systems simply ignore these associative spaces entirely. T-Mem is the first architecture to bring all 4 of these functional triggers under one unified system.
And, they don't even stop there. Outside of this main 4-part retrieval channel, they also added an overarching component called a persona module.
Right, I noticed that in the text. It's essentially a standing profile of the user, right?
Yes, the persona module operates as ambient context. It's a continuously updated per-speaker summary of standing traits, things like your occupation, your core hobbies, dietary restrictions, or even your communication preferences.
Okay, so how does it interact with the triggers?
Well, it doesn't compete with the triggers for retrieval. Instead, it's just always injected into the background of the AI's mind. It ensures the AI always knows exactly who it's talking to, providing a baseline context that fills in any gaps that specific trigger recall might miss.
Okay, so structurally, the theory makes a lot of sense. I mean, it's elegant, it's inspired by actual human cognitive science, and it explicitly targets the blind spots.
It does.
But, a beautiful blueprint doesn't mean the house won't fall down when you actually build it. Does this thing actually work when put to the test?
It works remarkably well. To prove it, the researchers used two major evaluation frameworks. First is Locomo, which tests standard long-term multi-session memory, and second is Locomo Plus.
And Locomo Plus acts as a sort of cognitive stress test, right? Like actively punishing systems that just skim for matching keywords.
Exactly. Locomo Plus specifically injects cognitive probes where the cue and the answer are bound solely by narrative or causal links, not by lexical proximity. It is designed to aggressively expose that associative blind spot we talked about.
All right, lay the numbers on us. How badly did the older systems fail, and how well did T-Mem actually do?
The numbers are pretty stark. Prior heavyweight memory systems like Mem-Miro, Memos, and HyperMem suffered a catastrophic drop in performance when moving from the standard Locomo test to the associative Locomo Plus test. We are talking about a performance gap of 28 to 50 percentage points.
It's a 50-point drop. Wait,
Yeah.
really? That means the moment you ask a question that requires actual human-like association rather than just simple word matching, half the time or more, the AI just completely loses the plot. So what was the gap for T-Mem?
T-Mem shrinks that cross-benchmark gap to just 5.45 percentage points.
That is a massive difference.
It is. It achieved state-of-the-art status on both benchmarks, scoring 80.26% on the standard Locomo and 74.81% on Locomo Plus. It empirically proved that the associative blind spot can, in fact, be closed.
But let me go back to the compute costs for a moment.
Okay.
Because generating all these triggers, the entity, the scene, the bridge, the horizon, plus constantly updating that ambient persona module, having the AI pause at right time to use its LLM weights to generate all these semantic connections, doesn't that cost an absolute fortune in tokens?
It's a very logical concern.
Yeah.
Usually adding metadata means adding cost. But the paper includes a really detailed efficiency analysis that proves otherwise. T-Mem actually achieves these higher accuracies while using fewer input tokens than heavily structured systems like HyperMem.
Wait, how is it using fewer tokens when it's explicitly generating all this extra metadata at right time? That seems counterintuitive.
It comes down to a top-down retrieval cascade.
Okay, what does that mean?
When it's time to actually answer your question, the read time T-Mem filters the search space in stages. It filters first by overarching topic, then by scene, and finally by specific item. Because these triggers act as incredibly accurate, highly descriptive signposts, the system doesn't have to drag massive, irrelevant chunks of your entire chat history into the context window just to hunt for the answer.
Ah, I see. It knows exactly where to look from the start.
Right. The triggers pinpoint the exact right memory immediately, meaning the AI only reads what it absolutely needs to. It basically trades a small upfront computational cost at right time for massive, highly targeted efficiency at read time.
That makes perfect sense. To really ground these numbers and show how this top-down cascade and the triggers work together, let's walk through a concrete example from the paper. Case 5, cognitive.
Oh, that's a great example.
Yeah, this is a real testing example that perfectly shows this magic in action. Let's set the scene for you. Imagine, months ago, you tell your AI assistant, I'm saving all my vacation days for one big trip because I want to spend a month exploring Japan's countryside.
A very clear, stated commitment. A classic item-level memory wrapped in a scene.
Right. Now, 6 months go by. You haven't mentioned Japan since. You haven't talked about vacation days at all. Today, you simply say to the AI, I've been spending my weekends visiting local historical sites, and it's surprisingly rich without needing a passport. Now, notice what wasn't said there. You didn't say Japan, you didn't say vacation, you didn't say trip.
And a traditional similarity search would look at the phrases local historical sites and no passport. It would likely pull up past memories about your local neighborhood or maybe a frustrating time you lost your ID at the DMV. It has absolutely no lexical or even direct vector reason to go looking for Japan.
But T-Mem nails it. The AI responds by saying, that sounds amazing. I remember how excited you were about exploring Japan's countryside, and it's wonderful that you're discovering cultural richness right in your own backyard.
It's brilliant.
How exactly did it make that leap?
This is the Horizon trigger at work. 6 months ago, when you mentioned Japan, the Horizon trigger didn't just log the geographical destination. It projected that scene onto forward-looking dimensions. Using its underlying semantic knowledge, it understood the implicit theme of your statement, which was a desire for rich cultural exploration.
So it logged the underlying human desire, not just the itinerary.
Exactly. So when you later cue the system with visiting local historical sites without a passport, the Horizon trigger successfully connects your current implicit theme of exploration without traveling far to that past commitment. It surfaces the temporally distant scene about Japan based entirely on associative relevance, not a single shared keyword.
It read between the lines, it remembered the feeling and the intention of what you said months ago, and applied it perfectly to today's context.
Yeah.
So what does this all mean for you and how you use these tools? To me, it means we are looking at the transition from AI being a static, searchable archive, like a really fast Wikipedia of your own life, into an active, engaged participant. It's an assistant that anticipates what you need, making the connections before you even know exactly how to ask for them.
It is the realization of episodic future thinking in silicon. By engineering the system to decouple reachability from evidence, Tencent has really proven that long-term memory doesn't have to be limited by the rigid words we happen to use. It can be defined by the meaning we intend.
Right.
And closing that cross-benchmark gap to under 6% shows this isn't just a theoretical white paper exercise, it's highly operational right now.
It's moving from the literal-minded filing clerk who needs the exact folder label to a true conversational partner who just gets what you're talking about because they understand your underlying logic.
If we connect this to the bigger picture, we really have to ask ourselves what happens next in this evolution. If AI memory is now being explicitly engineered to actively anticipate our future contexts through episodic future thinking, does this mean our AI assistants aren't just remembering our past anymore?
Oh, wow.
By predicting the exact context in which we might need information and surfacing it proactively based on latent themes, they are subtly guiding the flow of the conversation. Are they now actively shaping the paths our future conversations will take?
That is a wild thought. So instead of just fetching the parking garage for my old Honda Civic, it might realize I'm actually stressed about downtown traffic in general and suggest a totally different plan based on a conversation we had a year ago about preferring the train.
Precisely.
It's not just retrieving data, it's steering the interaction based on anticipated needs. That is equal parts incredible and honestly something I'm going to be thinking about for a while.
It's the profound difference between a reactive tool and a proactive participant.
So the next time your AI misses the obvious context, just remember, it's not you, it's the associative blind spot. But thanks to research like T-Mem, that blind spot might be a thing of the past very soon. Thanks for joining us on this deep dive.